Hi everyone, this is Héctor, your AFM expert at Nanosurf, and this week we'll be looking at ball pens. Ball pens, or at least the patent for ball pens, has been around for about 150 years. Over this period of time, the production of ball pens has evolved, and actually we got much better at making them. The problem is now the compliances are so tight that, believe it or not, atomic force microscopes are needed to produce these objects. The reason is that the roughness of the ball at the end of the ball pen, it's very important. If it is too rough, the ink might clog over there and might not actually flow. If it is too smooth, the ink might not be attached to the sphere, to the metal ball, and it might not flow either. So it needs to have a specific roughness to work properly. Today I'll show you how it looks like. And also I thought, what could be a nice Friday AFM experiment? Well, I can show you how the sphere, how the ball looks at the beginning, brand new, and how it looks after writing a little bit with the ball. Follow me into the lab. Actually, Nanosurf has been providing automated measurement solutions for roughness of ball point pens since 2008. So my next challenge is to figure out how to hold this and do AFM on it. The Industrial Solutions product has agreed where the steel balls can be placed and then fix it, and then they have specific locations. But for a Friday afternoon experiment, I need to come up with something smaller, quicker, and hopefully something where I don't need to extract the balls. So my first approach was to take this apart, have it like this, and then I just place it through the hole of the stage and scan it. But I couldn't find a nice way of gripping it, so I decided to cut it, obtain something like this. And this I was holding it with a pair of tweezers, something like this. This was on the sample stage. Usually it doesn't fall. It goes onto the sample stage, and I was able to move it and precisely put the tip on the right position. This worked pretty well for a while until it starts to drift a little bit. Probably it was not in a very stable position, and it was okay for a while, but then it was not. My first thought was to use something heavier and the same approach, but this didn't work either. And then I choose this. It's a piece of metal, looks like bronze, has a hole in it, and I can put a screw, and it holds perfectly tight. So press it here, and then it doesn't move, it doesn't fall down, and I can put it on the sample stage, and it works every time, and there is no drift. After mounting the sample, the next challenge is to align the ball bearing with the AFM tip. We do a rough alignment optically, and then we scan with the AFM, and we scan in two directions, along 0 degrees and along 90 degrees. This will tell us how far off we are in the X direction from the maximum, the top of the sphere, and also along the Y direction, where is the top of the sphere also. And then we just need to do a correction with the motorized stage. In terms of AFM imaging, these steel balls are not a big challenge because the surface is quite clean and it is hard. If something, one has to be careful of not damaging the AFM probe by using to a set point that is too low or a force that is too large, depending on the imaging mode. And for these images here, I'm using an NCLR probe in a dynamic mode, and I try to use a quite a large set point, 65, 70, 80%. To be gentle with the probe, I'm trying not to damage it too much, and use it through the whole experiment. Also, I'm trying to be gentle because there could be ink residues, and I am not 100% sure if they will stick to the probe or not. So I try not to indent into them. After capturing some images of clean, brand new and clean spheres, it's time to degrade them. Well, there is only one way of degrading. You have to use the pen, and use the pen until all the ink is gone. Lucky for me, I only have to do the first one because then I recruited the help of Clemens to use some of our automatization to make this process a little bit easier and a little bit more fun at the same time. And this, of course, created a new problem, which is now the ball is covered with ink. In order to clean it, I figured out that I can use a tissue gently tapping on the wall. And to avoid rotating the wall, I use an optical microscope and check that I was indeed not rotating it and covering it again with ink. And here again, there is no difficulty in this type of imaging. But it's worth mentioning that I'm using a feature here on Viewport, which is the Q. The queue lets you plan in advance several measurements, and if you are happy with the imaging conditions and you know which areas you want to image, you can prepare them in advance. So I wanted to do a zoom out, and as I zoom out, I reduce the scan speed and increase the number of pixels. So I ended with nice images with a decent resolution. And with the queue feature, I just simply start the queue, and the machine does everything by itself. And then I can go and do something else, like prepare the next Friday AFM. And this is the final result. On the left, you can see the wall of the pen brand new, as it came from the box. And on the right, you can see how it looks like after using the pen completely. You can see that it's full of scratches, basically. And it's no surprise that if some of these scratches are deep enough, the ink might actually flow through them, and you can end it with more ink on the paper than needed. It's worth noticing, for instance, that although the initial ball might have some holes on it, they don't extend along large areas. So they don't contribute to leakage like the scratches might do. It's interesting also that in some of the scratches, at the end of at the border of the scratch, the edge is flat. In some others, there is some material accumulation. This is a typical effect of indenting into metals. So there you go. You have your answer. This is how the ball pen ball looks like after using it. So for those of you interested in data analysis, here is how you analyze this data with video. When you first load the data, you will see that in the topography, you can see the sphere, and you can barely notice the roughness because of the large curvature of the sphere. So the first thing we need to do is we need to get rid of this curvature. And I'm going to show you two different ways of doing it, and then it's down to you to decide which one fits your needs best. The first way is by using polynomial subtraction. So we go to align rows, and then we use a polynomial, and we increase the degree of the polynomial until the final image looks flat. However, as you will see, it's not perfectly flat, and it still has some features on it. Second technique consists in generating a copy of the original image and then filtering it. So here is the copy, and then I use a Gaussian filter to just smooth out the fine detail, the roughness. And then I combine together these two surfaces by subtracting one from the other. We obtain a surface that doesn't have anymore the curvature of the ball, and is only the fine detail of the roughness. If we want further improvement, we can align row by row. So with the two images, one created aligning row by row with a polynomial, and the other one created with this sort of Gaussian blurring. Let's see how the power spectrum distribution compares. I'm just doing a little bit of playing a little bit with the color, so you can see that the one where we use the polynomial has still some large background features which were not completely smoothed out. If you are interested in these large features, then probably that's the technique for you. But if you are only interested in the fine grains, then you probably need to go for the Gaussian blur. To calculate roughness, one quick tool is, as we saw before in some previous Friday AFM, is to use a statistical function and select an area where you think you want to know the roughness. In principle, the area has to be large enough to contain relevant features. What I mean is, if you want to see the roughness of a trench, you need to include at least 2 or 3 times the length of the trench. You cannot just include a little bit on the bottom of the trench. Then you will not see the roughness of the trench. You can see that the values we are obtaining are slightly different, and you will see why they are different. If we go for the power spectrum density, and we calculate it for both surfaces, if you haven't checked the previous post about roughness, go and check it. It is explaining there the effect of different features on the power spectral density. What you can see is that in the polynomial one on the right, we have a lot of contribution for low frequencies on the left of the graph, while the one that has been flattened with a Gaussian blur has that part of the graph suppressed. And this is why when we calculate the roughness as a simple number, we obtain 2 different values. So now let's repeat the same process in mountains. We start by loading the data, and usually when you load a new data, it creates an interactive display, which I don't like too much. I prefer extracting channels. And the thing about channels is that you need to make sure you are importing the right one, and you're not selecting the other ones that you don't care about. In my case, I just choose the topography. Then you select the data itself, and you apply a filter which is the equivalent of the Gaussian blur we did in Videon. The difference is that in Videon you have to choose the number of pixels. In mountains you can choose the feature size that you are filtering out. Again, how much blur of features you filter out depends on your application. So with the new surface calculated, we can subtract it from the old one, and then we obtain the roughness of the sphere without the curvature of the sphere, as we did in Videon. The only difference is that here we get some edge effect on the edges of the image. So in order to get rid of that, we crop the data a little bit. You can either adjust it here, and then you make sure you're cropping out the undesired parts, or you can do some rough adjustment here, and later on you can adjust it dynamically, and the changes will propagate through your document to whatever quantities you calculate or whatever additional data you extract. So yeah, that's the new data, completely flattened. And now to calculate the roughness, you just go to the parameters table, and then you choose which surface is going to be used, and the standard you're going to use for the calculation, and which parameters you want to display. And then it generates your table automatically. If you were a ballpoint pen manufacturer, at this point is when you choose, by looking at the roughness, the different parameters, you choose if this ball is okay for production, or if it needs to be rejected. And now, by the way, I'm just making it look a little bit nicer by changing the color scale, by putting it in a new page, and by adjusting a little bit the axis, so the features are highlighted a little bit more. And here is to demonstrate that you can dynamically change the area that has been cropped, and then your resulting image changes, and your roughness does as well. So how to automatize this? You can select all of this, then go to mini docs. Sorry, I need to select it again. You go to mini docs, and then you create a new mini doc. So a mini doc is like a template that you can use to process data. Because I practiced a lot before recording this video, there is several mini docs with similar names. But you can put whatever name you want. You can draw your custom icon for it, or you can choose a default one. It's down to you. So then it opens this window with this sort of bluish border, indicating that it is now you're modifying a mini doc. As we don't need to modify anything here, we're happy with it. We just close it. And now it comes the fun part. If I want to process a new file, I have several ways of doing it. The first one will be to simply import the new file into an empty space, and with the new file selected, I go to mini-docs and apply the created mini-doc. I'm hesitating here because I created too many mini-docs previously, but yeah, that was the right one. And as you can see, it automatically processes this data, and it's telling us that it couldn't crop it properly. This is because it has very different number of pixels, so it's like the image has different size, much different. But that's okay. We identify that is the problem, and then we repeat this step and adjust it accordingly, and then voila, it is the new the roughness of this new data, calculated in the same way as the previous data. Yeah, or we can repeat the process. If there is no data at all, we can import the new data. Again, we select it and we apply the mini-doc. It repeats exactly the same analysis, and this time, instead of importing the new data and applying a mini-doc, what we're gonna do is I'm gonna replace the studio ball, because it turns out that I was not happy with this file. I made a mistake and I didn't import the right one, and I want a different one. So I simply drag and drop on top of the previous studio ball, and then this will apply the analysis here. In this case, we can see that the cropping becomes much smaller because this new data has more pixels than the previous one. So now you know something new about ballpoint pens. You know that it requires an AFM to produce them. And this is because the tolerances on the different parts of the pen are so tight that actually the roughness matter at nanometer scale, measurement that can only be achieved with an atomic force microscope. Here at Nanosurf, we produce automated systems that are capable of performing these measurements routinely. However, in this case, I wanted to show you the struggles, the challenges that you might face if you want to do the measurements in a standalone system. So what we have seen in this video is how to mount the pen, how to clean it, how to do data analysis on the measurements, and what was more interesting for me personally is the difference between a brand new pen or brand new ball and one that has been used. Here's the proof. One that has been used until all the ink was gone. So I hope you like it, and thank you for watching. See you next week.